ground state energy estimation using variational principle. Okay, so here's the problem we are tackling. Imagine a particle with mass m in a potential field described by V of x equals minus lambda times delta of x. Here lambda is a positive value. We are going to use a specific normalized trial wave function psi of x, which is given by the square root of alpha times e to the power of minus alpha times the absolute value of x. Alpha is a positive real constant. Our goal is to estimate the ground state energy of this system. By applying the ground state energy of this system, by applying the Fourier-Liel principle, you will see there are a few possible answers for this estimated ground state energy. They look like this. Option 1 is minus m lambda squared over h bar squared. Option 2 is m lambda squared over h bar squared. Option 3 is m lambda squared over 2h bar squared. And option 4 is minus m lambda squared over 2h bar squared. We'll figure out which one is correct. Alright, let's recall the variational principle. It tells us that the estimated ground state energy, we'll call it E for a system with a Hamiltonian operator. H hat and a trial wave function psi of x is given by the expectation value of h divided by the normalization integral of psi. The formula looks like this. E equals the bracket of psi h hat psi divided by the bracket of psi psi. Now the problem statement actually tells us that our trial wave function psi of x is already normalized. Super helpful because it means the denominator of the bracket of psi p psi, which is the integral from minus infinity to infinity of the magnitude of psi of x squared dx, is simply equal to 1. Therefore, we just need to calculate the expectation value of the Hamiltonian. That's the bracket of psi h hat psi, which means we need to calculate the integral from minus infinity to infinity of psi star of x times h hat applied to psi of x times. Let's write down the Hamiltonian for our system. For a particle with mass m in the potential V of x equals minus lambda delta of x, the Hamiltonian operator h hat is the sum of the kinetic energy operator and the potential energy. So h hat equals minus h bar squared over 2m times the second derivative with respect to x plus V of x. Substituting our potential h hat is minus h bar squared over 2 m times the second derivative with respect to x minus lambda times delta of x. Bit easier, we'll calculate the expectation values of the kinetic energy part and the potential energy part separately and then add them together. First up, the kinetic energy. We need to calculate the expectation value of the kinetic energy operator, which we'll call bracket t. That's the integral from minus infinity to infinity of psi star of x times minus h bar squared over 2m times the second derivative of psi of x with respect to x, all integrated with respect to x. Since our trial wave function psi of x is a real function, psi star of x is a real function, psi star of x is just psi of x. Is a real function, psi star of x is just psi of x times minus h bar squared of it. 2m times the second derivative of psi of x. The crucial part here is figuring out the second derivative of our trial wave function psi of x, which is the square root of alpha times e to the power of minus alpha times the absolute value of x. Let's calculate the second derivative of the wave function. The absolute value means we need to be careful, particularly around x equals 0. Let's look at the derivative for x not equal to 0 first. When x is greater than 0, the absolute value of x is just x, so our function simplifies to e to the minus alpha x. Taking the first derivative gives us minus alpha times the function, and the second derivative gives us alpha times the function. Now for x less than 0, the x laid times the function. Value of x is minus x, making our function e to the power of alpha x. The first derivative here is alpha times the function, and the second derivative is again alpha squared times the function. So you can see that for x not equal to 0, the second derivative is consistently alpha squared times the original function. We need to consider the derivative everywhere, including at x equals 0. The first derivative shown here involves the sine function and has a sharp jump discontinuity right at x equals 0. Looking at the limit from the positive side gives minus alpha, while from the negative side we get plus alpha. This means the size of the jump is minus 2 alpha. A key concept in distributional calculus is that a jump discontinuity in the first derivative introduces a delta function in the second derivative proportional to the jump size. Therefore, the second derivative is the expression we found away from 0 plus a term at x equals 0. Since the jump was minus 2 alpha, this added term is minus 2 alpha times the delta function of x. Let's calculate the second derivative of our trial wave function, psi of x. Starting with psi of x equals the square root of alpha times e to the minus alpha absolute x, we take the second derivative with respect to x. Using a result previously found for the second derivative of the exponential term, we apply this and multiply by the square root of alpha to get the expression shown. We then distribute the square root of alpha and simplify by recognizing the original wave function psi of x. Within the terms and combining the powers of alpha, we arrive at the final expression for the second derivative of psi of x. This is alpha squared times psi of x minus 2 alpha to the 3 halves, power times delta of x. This is the expression we will use in our kinetic energy integral. Let's plug this second derivative back into the integral for the kinetic energy expectation value. Bracket P equals minus h bar squared over 2m times the integral from minus infinity to infinity of psi of x times in parenthesis alpha squared psi of x minus 2 alpha to the power of 3 halves times delta of x, all integrated with respect to x. We can split this integral into two parts. Minus infinity to infinity of psi squared of x dx minus 2 alpha to the power of 3 halves times the integral from minus infinity to infinity of psi of x times delta of x dx. We have two integrals to evaluate now. Let's evaluate these integrals. The first one is the normalization integral we discussed. Since the wave function is normalized by the problem statement, this integral equals 1. For the second integral, we use the key property of the delta function. As shown on the slide, integrating a function multiplied by delta of x evaluates the function at x equals 0. So our second integral simplifies to psi evaluated at 0. Now, let's find psi of 0 using our trial wave function shown on the equal integral we using our trial wave function shown on the slide. We substitute x equals 0 into the expression. Since the absolute value of 0 is 0, the exponential term becomes e to the power of 0, which is 1. Therefore, psi of 0 is simply the square root of alpha. Now, substituting our results back into the expression for bracket t. The first integral evaluated to 1 and the second to psi of 0, which is alpha to the power of 1 half. When we combine the alpha terms, alpha to the 3 halves and alpha to the 1 half multiply to alpha squared. Simplifying the terms inside the brackets gives us minus alpha squared. Finally, the two minus signs cancel, leading to our kinetic energy expectation value. Next, let's calculate the potential energy expectation value, bracket V. That's the integral from minus infinity to infinity of psi star of x times the potential minus lambda delta of x times psi of x, all integrated with respect to x. Since psi is real, psi star is pi. We can pull the constant minus lambda out of the integral. So bracket V equals minus lambda times the integral from minus infinity to infinity of psi squared of x times delta of psi squared of x times the integral from minus infinity to infinity of psi squared of x times delta of x times psi of x, all integrated with respect to ios. Again, we use the property of the delta function. The integral from minus infinity to infinity of any function, f of x times delta of x dx, is just f of 0. In this case, our function f of x is pi squared of x. So the integral from minus infinity to infinity of psi squared of x times delta of x dx is just pi squared evaluated at x equals 0. Thus bracket V equals 0, thus minus lambda times psi squared at 0. We already found that pi psi squared at 0. We already found that psi squared at 0 is the square of x. The square of the square root of alpha, which is simply alpha. Substituting that back in the potential energy expectation value is bracket V equals minus lambda times alpha. So minus lambda alpha. Now we combine the kinetic and potential energy expectation values to get the total energy expectation value. According to the variational principle, this gives us an estimate of the ground state energy, and it depends on our variational parameter alpha. So E as a function of alpha, E of alpha is bracket T plus bracket V. That's h bar squared alpha squared divided by 2m minus lambda alpha. This expression clearly depends on alpha. This were divided by 2 minus lambda alpha. This expression clearly depends on alpha. The variational principle tells us that this energy, E of alpha, is an upper bound for the true ground state energy. To get the best possible estimate, we need to find the minimum value of E of alpha by varying alpha. To do this, we'll use standard calculus. We'll take the derivative of E of alpha with respect to alpha set, that derivative equal to 0, and solve for the value of alpha that minimizes the energy. This optimal alpha will give us the best possible estimate for the ground state energy. Using this trial wave function, let's calculate that derivative. We need the derivative with respect to alpha of the quantity h bar squared alpha squared over 2m minus lambda alpha. Taking the derivative of the first term, the alpha squared becomes 2 alpha. So we get h bar squared over 2m times 2 alpha. The 2's cancel, leaving h bar squared alpha over m. Taking the derivative of the second term minus lambda alpha with respect to alpha just gives us minus lambda alpha. So the derivative of the second term minus lambda squared alpha over m minus lambda. Now we set this derivative equal to 0 to find the minimum. We have h bar squared alpha over m minus lambda equals 0. Rearranging, we get h bar squared alpha over m equals lambda. And solving for alpha, we multiply both sides by m and divide by h bar squared. This gives us the optimal value for alpha equals m lambda over h bar squared. This is the value of alpha that will minimize our estimated energy for this specific trial wave function. The final step is to substitute this optimal value of alpha back into our energy expression, E of alpha, which was h bar squared alpha squared over 2m minus lambda alpha. Substituting m lambda over h bar squared for alpha, the minimum energy E minimum equals h bar squared over 2m times the square of the quantity lambda over h bar squared minus lambda over h bar squared. Let's square the term in this lambda over h bar squared. Let's square the term in the parenthesis m lambda over h bar squared. Lambda squared over h bar to the power of 4. So E minimum equals h bar squared over 2 m times m squared lambda squared over h bar to the power of 4 minus m lambda squared over h bar squared. Now we simplify. In the first term, we have h bar squared in the numerator and h bar to the power of 4 in the denominator, leaving h bar squared in the denominator. We have m squared in the numerator and m in the denominator, leaving m in the numerator. So the first term simplifies to m lambda squared over 2h bar squared. The second term is already simple, minus m lambda squared over h bar squared. So E minimum equals m lambda squared over h bar squared. So E minimum equals m lambda squared over 2h bar squared minus m lambda squared over h bar squared. To combine these, we can write the second term with a denominator of 2h bar squared by multiplying the numerator and denominator by 2. That gives us minus 2m lambda squared over 2h bar squared. Now they have a common denominator. E minimum is m lambda squared minus 2m lambda squared all over 2h bar squared. This simplifies to minus m lambda squared over 2h bar squared. So the estimated ground state energy we found using the variational principle with this trial wave function is E minimum equals minus m lambda squared over 2h bar squared. Now let's compare this result to the options we were given at the beginning. Option 1 was minus m lambda squared over h bar squared. Option 2 was m lambda squared over h bar squared. Option 3 was m lambda squared over 2h bar squared. Option 3 was m lambda squared over 2h bar squared. And option 4 was minus m lambda squared over 2h bar squared. Minus m lambda squared over 2h bar squared matches exactly with option number 4. The estimated ground state energy is indeed minus m lambda squared over 2h bar squared. This corresponds to option number 4, and that's option 4.